Hello everyone, today we're going to be looking at usaco-training fence loops. Okay, so in this problem we're given n fence segments numbered from 1 to n. And we know the length of each segment, the segments which connect to it at one end and the segments which connect to it at the other end. And no fence would connect to itself. Alright, so what we're going to be doing is that given a list of these fence segments, we're going to compute the smallest perimeter of any pasture. Okay, so what's a pasture? And a definition of a pasture in this problem is that it has to be some kind of like cycle. Okay, so for example, over here, if you have something like use this one, use the one with length 10, and you use this one and this one, this would be a valid pasture because everything is connected together and they basically form some kind of like polygon. Okay, and this would basically work because this, you can think of it as this could act as some kind of fence, so then some cows inside would not be able to get outside. But then if you have something like 4, 5, 6, this would not work because it does not like fully contain some area. Okay, so since we want the smallest perimeter in this diagram, the best choice would be to be taking this 2, 7, and 8. And the total perimeter of this would be 2 plus 8 plus 7, which would be 17. So now let's take a look at the input. At first glance, this may seem kind of confusing, but I'm just going to describe it. So over here, we have n, the number of line segments. So following this, we have basically n groups of data representing the description of the line segments. Okay, so basically every 3 lines, okay? So let's look at the first line segment. First integer is going to be the ID of the segment. Okay, so over here it's just going to be 1. Second number is going to be the length of the segment. Okay, so the length of this is 16. Okay, third number is going to be the number of connected line segments on one end. It's basically what we described here. And our fourth integer is going to be the number of segments that are connected to our other end. Okay, so there's 2 segments that are connected to the other end of segment with ID 1. So then our next line is going to be the ID of those segments that are connected on one end and the other end as well. So that's it for the segment number with ID 1. So this is going to be applied to the segments, each containing 3 lines. Okay, so I'll actually draw this out, so don't worry if you don't really understand it now. Okay, so let's look at our output. We just have to print a single line containing a single integer, which represents the shortest surrounded perimeter. All right, so let me draw it out. So first segment we have is 16. Okay, so we have our length of 16. Okay, so to the front we have segment 2 and 7, and to the back we have 10 and 6, so I'll actually draw that later. Okay, so for segment 2, we have segment 1 connected, and the length of segment 2 is going to be 3. Alright, so this is going to be 3. Okay, so for segment 3, it's also connected to segment 2. Okay, so we have segment 3. And the length of this is also going to be 3. For segment 4, it's also connected to segment 3. And its length is going to be 8. Alright. For segment 5, let's take a look here. It's connected to segment 4 on the front. And the length of this is going to be 10. Okay. For segment 6, okay, so it's connected to this and that, and okay, so it's also connected to segment 1. So let's first draw it as connected to 5. So this is our 6, and the length is 6. And to the back, it's also connected to segment 1. So that's the start and that's the end. So we also draw a line here. And this, okay, so let's just this is actually a bad drawing. Let me think how I should draw. Alright. So let's just say that this is connected. So if we do this, we can just do 6. Alright, easier. Okay, so that's for our 6. Okay, so for 7, it's going to be connected to 1 and 2 from the top, from the over here. So it's going to be connected to this point basically. And so let's just draw that. We have our 7, and the length is going to be 5. Okay, so for 8, okay, that's going to be a lot more confusing. Okay, so for 8, it's connected to segment 2. Okay, so if you look back at the input, it's going to be over here. Alright, so to over here, and that's going to be the first part. So this is segment 8 with length 4. Alright. And besides that, it's also connected to segment 7 on the end. So you can basically draw it like this. Have this, whoops, crayon. Like this. And the length is 4. Oh, okay. That's cool. Okay, so that's for 8. Let's take a look at 9. So first thing is that it's connected to segments 7 and 8. So this is 7 and 8. We have one number and a points here. And it's also connected to 4 and 5. So we have 1, 2, 3, 4, and 5. Okay, let's draw that. And that's going to be our 9. So what we have is, this is our 9. And the length is 5 for it. So for 10, our final segment. Okay. So in the front, it's connected to 1 and 6. 1 and 6. Okay, so that's one of our endpoints. And for our second one, it's going to be 4, 9, and 5. Going to be over here. So we draw a line, and this is going to be length 10. Alright. So this is going to be how the graph is going to be looking like. And let's figure out the best solution. So just taking a quick glance, the optimal solution would be taking this. So you take 3, 5, and 4. So our perimeter would be 3 plus 5 plus 4, 12, right? So that's just it for the diagram, but like, how are we going to solve this? So the first thing that we can do is that, it's kind of hard to, build this graph, okay? So then, what you're going to do is that, okay, so for each segment, okay, so we have our segments. We basically have tens. I'm just going to draw 5 over here. Alright, so we have our segments, okay. What we can do is that we can make some kind of like 2 extra nodes, okay. So we make 2 extra nodes. Let's actually use green, or let's use right here. And for each of these segments, we're going to link these 2 nodes. Okay, so for each segment, we're going to store 4 nodes, okay, since we're also going to have these as well. Okay. And we're going to link the weight between these is going to be whatever weight we have for our, or the length actually for our segment. So that's it for our weight. And now, since we're basically calculating the perimeter, then adding an edge with length 0 wouldn't matter. So for all of these, we're just going to give them a weight of 0. Or I actually kind of rephrased that wrong. So let's actually, okay. So we actually only need 2 nodes, just the weight between these, okay? Alright, let's delete that 2. Delete, 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 and delete, or delete these 2, or so then, okay, so actually we just need to keep track 2 nodes for each segment, okay? The start and the end, okay? So now how are you going to link, link the nodes together? Okay. So then, let's just say this is 1, 2, 3, 4, and 5. Let's just say we're linking 1 and 4. We're linking the front of 1 and the end of 4. What we can do here is that we can just create another edge, because, like, if, like, in, like, the diagram over here, it'll just look something like this. So we have basically 3 points, but it's kind of, hard to keep track, or hard to, merge these points together. So what we're going to do here is that we can create another edge, okay? And since we want the perimeter, we can just make this weight 0. So this wouldn't affect our area at all. So then everything would run good. So then if we're like also creating another edge, we also make this 0. And basically when we link 2 segments, we're going to create an edge with weight 0. Okay. So now basically what we're going to have here is that, so right now this is our 1. We have our other nodes. So then we're just going to link these together, like each with weight 0. Okay. And notice that, this wouldn't basically affect, the requirements for our perimeter as well. Okay. So now we kind of have, another graph that looks like this. So then what we're going to be doing is that we're just going to, kind of brute force the shortest perimeter. Okay. So I'm just going to assume that you've done this, so the points wouldn't, lie on the same thing. Alright. So then we just pick any node, okay? So let's pick this node. We're going to try moving this direction, keeping track of which nodes have been visited and which nodes haven't been visited. So let's just say we move along this edge, okay? So now we're at this node. We can choose to go in any direction. We go to this node, but we can't go back, okay? So then we go to this node, and we find out that, whoa, we visited a node that we have like visited before. So then what you would do is that you would mark this as you would update your answer, or relax your answer. So then your new answer may become something like 26. Okay. Then after this, we're going to undo this. We're going to undo this. Now we're at this node again. And from this node, you may want to go to something like this node. All right. And from this node, you may want to go something like this node. And once you go back, you relax your answer with the new distance, and you would just basically keep on, keep on searching this, okay? So when do you know to stop? Okay, so you basically want to stop, when you've like reached a node you have visited before. So for example, if you start here, you go here, 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 back. Okay, so you update your answer. But the thing is that like running this whole thing may take kind of too long. So we may need some kind of like heuristics to speed this up. So what you're going to do is that we're going to have our answer, which is going to be our current answer, or current mean perimeter. So anytime we reach a node with distance greater than answer, we can just return, or we can just like terminate search. And this is because like if you already have some kind of current perimeter that's already greater than answer, there's no need to search this again, or keep on searching, because the new possible perimeter is always going to be greater than this answer already. So then I think this is basically the only heuristic you need to pass the test. And so I'm just going to kind of sum this up. So first thing is that to create the edges, we just link the node and the other node with a weight of 0. And after that, you just, from each node, you make a depth first search from that node, and you search basically all possible outcomes from that node. Okay, so let's get to coding. Alright, so over here, let's get this like that. Alright. So let's get my template in. Alright, so what we have is that int n, which is going to be the number of segments. And following this, we're going to have the ID of each of our segments. Okay. So remember what I said, that we have to have 2 endpoints for each segment. So then what we can do is that we can kind of pre-compute this. So for I from 1 to n, we're going to have our ID. So our maximum n over here would be 2 times, or just 100, 105. Alright, so we're going to have our ID n, or max, 2. Okay. Oh, okay. So to generate this, we can have our first endpoint equal to 2 times I minus 1. And we can have our second endpoint equal to 2 times I. So then this would generate the numbers from 1 to 2 times n. Okay, so since at the nth loop we're going to have 2 times n minus 1 and 2 times n, which is going to fit perfectly. Alright, so now we're going to loop through, let's just call this j from 1 to n. We're going to have our I, and we're also going to have the length of this, so let's call this w. And we also have the sides of our number of segments containing our left and right correspondingly. Okay. So then, one thing you may notice is that, for example, you have our one. Okay, so now it says, okay, we need to connect to the second segment. But we don't know like which side it's going to be connected. Okay, so what we know is that we know that segment 1 is using the first side to connect to segment 2. But we don't know like which side or which side on segment 2 that we're connecting to. So we can have our map, which is going to be like which side we're going to be connecting to. So okay, so what we're going to do here is that you have our 2. Okay, so we read in our 2 and we don't know what to do right now. So we just make sure that when we're doing our 2, we need to know that next time when we're looping through our second segment, we see a 1, we have to connect it to the first side. So then we can use a map. By default, we should just memset it back to 1. So now we have weights, and then we can have our M0 and M1. So now we can just int this. Alright. So now what we're going to do here is that we can kind of create some kind of link functions. Okay, so to create an edge. Okay, so we have our link I, j, and weight. So besides this, we also need some kind of like adjacency list. So we can have a vector. Ooh, that's weird. So we have a vector of pairs of integers. Let's actually use this first and second. Alright. Let's call this ADJ, and the maximum number of nodes we have is mx times 2, which is about to be 100 times 2, since we're allocating 2 nodes for each segment. So over here, we just do ADJI dot pushback JW, ADJJ dot pushback IW. Okay. So now, first thing that we're going to do is that we're going to create an edge between the two nodes. Okay, so over here, as I said before, if we have an edge, so let's circle this. We're creating an edge of length w between these two. So then, what we're going to do here is that we're going to link. What's wrong here? Oh, this is a void. So we're going to link IDI 0, IDI 1, W. Okay, so that's just for our internal segment. And now what we need to do is that we need to loop through these M0 for our M0 and for our second end. So let's loop through, or we can just do rep M0. We have our, let's just call this K, okay? So if we already or if nothing is declared before, so if map of ik is equal to -1, then we're going to set map ki equal to 0, since we're making it on the first end. Otherwise, we're going to link IDI 0, since M0 means the first end, and IDK, and we already stored it in our map, so it's going to be map ik. And the length is going to be 0. And similarly, we're going to do the same for M1. So over here, we're going to set to 1, and here as well. Alright, so let's see. Link. Okay, so everything's good. Alright. Okay, so now we're done reading our input, so we can start, actually doing our search. So we have our answer. And by default, we can just set it to a pretty big number. We can just give it mod. So now for each of our I from 1 to 2 times n, first thing that we're going to do is that we need to have some kind of visited array. So we can just give it a bool. Let's call this v. Going to be max times 2 because that's going to be the number of nodes we have. We're going to memset it every time since we're basically resetting the search. And then we're just going to DFS from I. Alright. So we haven't declared that yet, but we're going to. Okay. So we have our DFS. We're going to I is our current node. What we need to also have is our parent, since we don't want to, go back to our parent. And we also have to have the distance, okay? So that's going to be what we need to have our answer. So we also have 0 and 0. So if, to speed this up, if D is greater than answer, we can just return since, we don't have to keep on searching. Otherwise, we're going to loop through each edge that we have. If E.first, which is going to be the node, is not equal to our parent, then we can, go depth search. Okay, so first thing here, we need to set visited I equal to true. So what we can do is that we can just set visited of I equal to true. So over here, if we already visited this node before, so if visited E.first, our answer, we can just minute answer and E.second, which is going to be the weight. Or actually, okay, so yeah, so we do actually have to add that. So this is going to be D plus E.s. Otherwise, we're going to set this to true. We're going to search this node, so E.first, I, and D plus E.second. And then we're going to set this to false. Okay. Let's see what's wrong here. Okay, nothing's wrong. Alright, after we just print our answer. Alright, so let's run this fence 6.cpp. Alright, it's running. 0. Okay, interesting. If v E.first, we're going to print that out. Answer, we just set it to a big number first. Nothing should be wrong with that. I D plus E.second looks right. So we can set root. We can set I. Okay, so that's going to be our root. And then over here in here we can just debug IPD. So let's test that out. It's compiling. Alright, interesting. So what I'm going to do here, what's the warning? Interesting. So if we're going to do this, we're going to print updated. Okay. So it may be kind of, easier to debug where is it from. Here's our updated. Okay, so I'm just going to remove this debug line. So I can run this more clearly. Okay. It's running. Alright. So, okay. So I equals 1. Turns out you do update a lot of things. Alright, interesting. So link ID I1, ID I2 with weights. Loop through each of these, read K1 since it's our one end, and we do link these. And we loop through from 1 to 1n, and we try to do it. Alright. So, let's take a look. P. So right now we have our P, and we also have our D. So let's just print IPD. Okay, so we have our D, and our D is, often a 0, which I don't think should be correct since we are adding, we are like accumulating this. Okay, so let's first look at I equals 1. Ooh, okay, so that's damn a lot. Alright. So 1, 0, 0 looks correct. 2, 1, 16 also looks correct. 12, 2, 16. Okay, so looks like we've gone to 12. Also looks correct. 22. Okay, so after we reach this 44, we marked it as updated. Alright. So then, I'm just going to set that, if, so basically if e dot second, or if, d plus e dot second is greater than 0, then we're going to seek him an answer in d plus e dot second. Otherwise, we're just not going to take it, because there might be some issues with that. 3. Wow. Okay, so 2 times I minus 1, 2 times I. And our map is equal to -1 by default. That's great. And every time we link these two, we have a 0. Let's see what's wrong. So we're checking, because if this is visited, if it's not equal to its parent. Oh, okay, so it may look like we do have some kind of mini cycles between these 3 points. So then, what we can do to do this is that to kind of like eliminate this case, or let's actually first draw it out. So, as I mentioned here, let's just say we have this point, okay? So what's going to happen is that we have our three segments. So we have, let's actually use red. So we have this segment, and this segment. So you can visualize as these 3 points, and there would be an edge between all three of these. So then like you could just walk this within length of 0. Okay, so let's go back. Okay, so to get rid of that case, what we can do is that not to basically judge, like to do this so quickly. Okay, so instead of basically DFSing from each node, we want to DFS for a cycle that starts at I and end at I. So then over here, instead of having this, we can have our I and I. So let's actually call this J. So what we want is that we want to have a cycle that starts from I and ends at I. So then to do that, we can have this. Okay, so we also have to check that it's not visited. Then we can do this. Okay, so interesting. DFS. Alright, so over here we also have to add that too. Okay. So if D is greater than 0, meaning that we have like actually traveled some distance, not just like stay there, and J is equal to I, then we can CK min D, our answer in D. Okay. And we can also return, since we can just return this as well. Alright, so let's actually check that again. Okay, running. Okay, so that's a pretty big number. And J is equal to I. J, E dot first. I. That looks good. Not E dot F. 0, 0, I. Well, I guess we can kind of debug this, so we can have our JIPD. Okay. So let's try that again. Ooh, okay, that's a lot. Huh. Oh, okay, so I think that we're not actually executing that because over here I set I to be visited. And once you reach here, if it's not visited, you go in. Well, that's a dead end. So over here, we actually have to set I is equal to visited. So if I is visited as well, then we can do this. Alright. So let's run it again. Ooh, a 0 again. Huh. Interesting. So we're calculating distance to start and end at each node. Let's just put D greater than 0 again too. Alright. E dot first, E dot second, that looks great. 12. Oh, okay. So what I made sure here is that you can't have a distance of 0, okay? Because as I described here, what we're doing here is that we have 3 nodes, okay? And we're creating an edge between all these. And the weights are 0. So we have to make sure not to count this case. Because if we do, our answer is 0, but what we're actually doing is that we're on the same node. So besides that, we just need to check that distance has to be greater than 0 to update our answer. Alright, so let's submit that. So we can set in fence 6.n and set out fence 6 style. Alright. So I don't think we printed anything, so let's just submit that. Alright. Let's send it in. Ooh. Oh yeah, okay. So oops, I did not add this fence 6 and language C++11. Alright. Ooh, okay, so everything is correct. So that's it for today. If you have any questions, feel free to leave them in the comment section below. Thank you. Bye.